Here's Valentin and Dikist.
So actually, I'm going to just talk about Dickies here because it's much more straightforward, as you just said. So thank you for giving NSO this opportunity to provide an update on the status of the Daniel K. Inouye Solar Telescope. This picture is 2 days old, and as you see, lots of progress at the summit. We've been working hard this summer on enclosure erection. The domed enclosure is pretty much as tall as it gets. The telescope doesn't get any taller. And we're working hard to finish the enclosure. As soon as it is finished, Dickies from the outside will look like the final result. Of course, there will still be a lot of work that is needed inside for the telescope and a number of things I'll say at the end of my presentation. My presentation has two parts. On the second part, I'm going to be addressing Dickies and actually how much HAO is involved in Dickies. HAO and NSO have had a long history of collaborations. I learned yesterday that there was an American airline plane full of HAO and climate scientists that found the place for sunspot. That was a surprise to me. So this collaboration is from the very beginning of NSO, but it continues today. HAO is heavily involved in the construction of Dickies, as you'll see at the end of my talk. The first part of my presentation is more a personal experience. As Greg said, I was a former HAO postdoc, and when I was a postdoc here, and that's 20 years ago, I was able to witness what I want to call a paradigm shift. Thomas Kuhn famously said that science progresses through paradigm shifts of various magnitudes. The one that I saw and that I live here at HAO changed the way in which we design solar telescopes, and I think Dickies benefited from this paradigm shift. You'll see what I'm talking about. So let me show you this picture. It's a pretty picture. It's from AIA, it's from SDO. It's beautiful. Everything that you see here that is nice, whether it's dark or whether it's bright, is all magnetically related. It's some magnetic configuration that will create all of these beautiful structures at the surface of the sun. So the obvious consequence from these pictures is go and measure the magnetic field of the sun. But actually, this is really hard. And yesterday, Bruce Lights and Andy Skumanich were telling us how difficult it is. The sun doesn't help at all. The way you measure the magnetic field is through polarization. And the sun never produces 100% polarization, produces tiny fractions of polarization. And actually, the mapping between polarization and magnetic field is not linear at all. There is a lot of physics in between. You need to put radiative transfer, you need to put atomic physics, you need to put Zeeman scattering processes. So it's really hard. It's not linear. You need to understand that to be able to do this mapping. And on top of that, the sun produces tiny fractions of polarization, and it's hard to measure. So this is why I think it took so long for solar physicists to understand we need to measure the magnetic field in as many places as we can. Actually, that explains, in a way, that's how SOHO was the way it was. Let me say something about SOHO. SOHO, I think, is the space mission that was more relevant for our field. I think I have published myself more papers with Inouye than with SOHO, but actually SOHO changed really our field. It did real progress in the interior, in the corona, and in the solar wind. SOHO had 12 telescopes, 12 remote sensing instruments looking at the sun. None of them was prepared to measure the magnetic field, okay? None. There was just one that was prepared to measure something else as primary objective, the velocities, which was NDI, that actually someone at NDI said, well, if we turn this around, we can also measure the magnetic field. But if you go to the SOHO book, which is 800 pages explaining all of these 12 instruments, there will be just one paragraph about measuring the magnetic field. This paragraph in here, 800 pages, just one paragraph about measuring the magnetic field on the sun. Why? Because at that time, everybody was doing this from the ground, and NSO was doing this from Kitt Peak, and it was thought to be really hard to do from space. So actually, none of the instruments on SOHO was prepared for that. But those of you who have seen the success of SOHO know how important NDI magnetograms were. Every of the other 11 instruments were using SOHO magnetograms for the context, to understand what the magnetic context was. It's just one paragraph. And I always found this really interesting that there was just this one paragraph in here. That's 95, that's when SOHO was launched. But of course, this mission takes 10 years, so it was decided about in the process of 10 years before 95. What was going on the ground was that in 92, HAO deployed the Advanced Polarimeter to the Down Solar Telescope in SACP. And you heard a lot about the ASP yesterday. Bruce gave a lot of explanations about the successes that were provided by the ASP. There were a lot of new things that were brought in. There were new calibration optics, new modulators techniques. Here you see some of the instrumentation. Looks like all exabytes for getting the data somewhere. That's the telescope in Sunspot. This is one of the papers we published. This one was actually published in Nature, so I think it was pretty successful. But the point here that I want to make is that the telescope where the ASP was put was not really prepared to do polarimetry. Why do I say that? Well, the reason for that is that because every time you hit a mirror at an angle, you change the polarization of the light, and that's what actually maps into magnetic fields. So as Bruce was saying, this is the solar light. You hit here at 90 degrees, you are changing the polarization. You hit again here at 90 degrees, you are changing the polarization. Actually, what you measure at the end has really nothing to do with what came from the sun. It can change by as much as 100%, okay? That's what happens. So you need to sort of trace back what the telescope is doing and go back into the sun. How was the ASP able to be so successful? What we did was, and that's the elevator there. Now that I am the NSO director, I've been told not to call this the elevator because we don't have the safety measures that should have to call it an elevator. It's just a working platform. So Bruce and I, what we did was we took the working platform and we put this linear polarizer at the entrance of the telescope. We just put it there. It's not there when you're observing the sun, but you put it there, you polarize the light in ways that you know, and you follow this for a day. And this is a day measurements. This is from the paper that Andy Skumanich led for calibrating the telescope. And with these measurements, because you know what you are putting and then you know what you're measuring through nonlinear least square and through fittings, you now know what the telescope is doing. Then you take out your linear polarizer, you point to the sun, but now you know what the telescope is doing. So this is what the ASP did that sent the message to the community saying we now know how to calibrate to some level of degree of accuracy. We now know how to calibrate solar telescopes. And that's the change of paradigm that I was talking at the beginning of my talk, because some of you might remember that what solar physics was doing was trying to build polarization-free telescopes. There was less was trying to do. The first thing they wanted to do is to measure the polarization of light as soon as possible before any folding mirror, because they're going to change the polarization. So they decided to put it in here as soon as possible, this polarimeter. TEMIS did something similar, but they paid a big price. LEST, for example, was getting rid of 50% of the light just by putting the polarimeter in here. TEMIS had both beams through the system, but both beams through the system went through different optics, different gratings components, and in the end, it was as hard to combine them into one realistic measurement as to do the polarimetric calibration of the telescope. So this is the paradigm shift that I think I was able to see and to participate when I was a postdoc here at HAO. After all of these calibrations, ASP said, well, we know how to calibrate telescopes. You don't need to make them polarization free, you just calibrate them. And I was very proud to participate on that. And actually that was transferred to all of the solar telescopes in the world. I then went to the Canary Islands and I helped calibrated the Schudis Tower, which is very similar to the Dan Solar Telescope in SACTI. That's the first polarimetric calibration of the Schudis Tower with 0.5 meter, with 1 meter. They're doing something similar, and these telescopes are now calibrated. The VTT in Tenerife is also calibrated. You go there with your 1 meter aperture linear polarizer. You put it there, you rotate it, and you understand what the telescope is doing. The Gregor telescope is a different thing, but it actually follows also what the ASP said you have to do. The Gregor is just now putting calibration optics at prime focus, and you calibrate the entire telescope. This effort actually was translated into space. Here you have our Inouye colleagues with their polarizer, putting it on top of Inouye to calibrate the telescope, the same thing as we were doing with this working platform at the Dan Solar Telescope. Similar things for HMI SDO. It's a smaller instrument, but the same polarization calibration techniques as they were developed for the ASP. I myself participated into the magnetograph. I was the PI of the magnetograph for the Sunrise balloon, and I followed a very similar scheme as what the ASP was doing for the calibration in here. But HAO was part of Sunrise. Here I have the 2009 flight. Sunrise flew twice. This is the 2009 flight. This is the 2013, and here we have one of our host scientists in front of the telescope. That's after landing. As you can see, we were just showing that the mirror didn't break and that we could fly again. The participants in this Sunrise project was MPS. MPS built the telescope. HAO the gondola. I see myself, I was the PI of the magnetograph, and I'm there. I apply all of these calibration techniques that I was explaining at the beginning of my talk. And Kiepenheuer, the tip-tilt mirror, the image stabilization system. So one of the results from IMAX Sunrise is this animation here. And I think this is still state-of-the-art polarimetry. What you do see in here is the continuum of the sun, so that's the surface of the sun. These are Doppler motions. You see the PMOS in here, and these are the two components of the magnetic field. This is longitudinal component, it's vertical, pointing up or pointing down into the sun, and you've seen this before. But this one that was really new from IMAX. Bruce Light yesterday said that for the first time, the advanced Stokes polarimeter was able to measure the horizontal component of the quiet sun fields with the ASP, and actually I co-authored that paper. And that was with a slit instrument. Then when Inouye did even with better resolution, even with better sensitivities, and much more thorough characterization of the horizontal fields, but we never had an animation of these horizontal fields. These same horizontal fields that were measured with the advanced Stokes polarimeter are the ones you see evolving here. And we were able to then, thanks to everything that I learned here at HAO, do the right calibration. If you make a mistake in your calibration, what happens is that these two components of the field get mixed. And it's really hard to get them separated. But with good calibration, you can do it, and you have here the longitudinal and the transverse field well separated in the same way as we did it for the advanced Stokes polarimeter. So as I said, this is a state-of-the-art. Let me give you some numbers for what do I mean by state-of-the-art. So this is 100 kilometers. The resolution of what you just saw is about 100 kilometers. The cadence, the temporal cadence, is about 1 image a minute. And the sensitivity, this is the sensitivity to polarimetry. This is how much you will measure. If you have here 10 to the 3 is that one photon that is polarized out of 1,000, you're going to measure that. Okay, that's what this number means. But actually, because of the size of the sun, we know that we need to improve on some of these numbers. We need to improve on all of them. And Dickies will allow us to improve all of them. But the combination that I'm going to use here is I'm going to stick to 100 kilometers. There is a lot of science that we still need to do at 100 kilometers. 100 kilometers is the scale height, is the photon mean free path. So it's a very interesting physical scale of the sun. I'm going to improve on the time resolution because everything moves too fast on the sun. We actually know that depending on what you use, but for granulation, you probably don't want to spend more than 25 seconds, and actually polarimetry makes things difficult, so you can only expose for about 6 seconds instead of half a minute as we have here. And we also want to improve on sensitivity. We want to measure one polarized photon out of 10,000 because there are physical processes on the sun that just polarize that little. So you put all of this into the equation that tells you what is the telescope that you need. You just put it there. And actually, you have to put how bright the sun. And I need to convince my nighttime astronomer colleagues that we need a 4-meter class solar telescope. So I put these units in what they understand, this magnitude per square arc second. I don't understand that units, but I know it's right, because when I transform it into more physically relevant units, I get the right number. So that's how bright the sun is. And when you put everything together in here, you get 4.6 meters. That's what you need if you really want to have 100 kilometers, few seconds, and 10 to the 4. And of course, this is a driver for the Daniel K. Inouye Solar Telescope. Spectropolarimetry, and for me it's not difficult to pronounce this word. I can pronounce spectropolarimetry several times, and I will in a second. It's a major driver for how the Dickies looks the way it does. Okay, we need to do imaging spectroscopy, polarimetry of things that change very fast, and that's why we need these 4 meters, as I had just proved to all of you. But we also want to do coronal magnetic field measurements, and that's this component here, clear aperture coronagraph. How do we do that? It's a Lyot coronagraph. As we heard yesterday, we do have a Lyot stop. We're going to measure the corona as well, but we have a clear aperture. So that means our mirrors are off axis. So we hit the mirrors at an angle, and what it will do is change the polarization. Are we scared of these changes of polarization? David is saying yes, I'm saying not that much, because we know we can calibrate that. ASP told us you can calibrate these telescopes, okay? And David knows how to do it much better than anyone. Here, these are the co-institutions of the Dickies, NSO is building Dickies, but we have the community engaged on the project, HAO and GIT, and the University of Chicago and the University of Hawaii are the 4 co-institutions of the Daniel K. Inouye Solar Telescope. The telescope is on budget, is on time. First light will be September 2019, and as you see, real progress. This is actually a bit older than the one that I showed first, but there is progress elsewhere. This is the telescope, and if you can hear the sound, this sound is the real sound of the telescope as it moves, okay? That was built at the factory at Ingersoll in Chicago, And the off-axis component that I mentioned can be seen here. This is the primary mirror. Here, it's covered. There is no primary mirror, actually, here. It's just the telescope going through factory acceptance. That's the secondary. So the light from the sun comes here, and it hits at an angle, goes to the secondary, and at an angle goes inside the telescope. Polarization is going to be changed, but we know how to measure all of these changes of the polarization of the telescope. Okay. Someone said something? Oil, yes. Mercury, not. Okay. So I guess. So well, okay. So I don't know what is that. Is that PowerPoint? Okay. So there's no proxy needed. So here you have the off-axis reflection. Okay. So it goes down, and all of this will change the polarization of the solar light, but we know how to calibrate this to some level of accuracy as required from the science. Here you can see all of the work we need to do inside. So the outside will be finished. We need to bring the telescope. We need to bring the instrument platform in here. So there will be a lot of work that is needed for a couple of years once the outside part of the telescope is complete. The telescope comes with instruments, with 5 first light instruments. HAO is doing the imager. It's also the instrument we're planning to use for the commissioning, just to see how the telescope focuses and how our adaptive optics system works. But look at the other 4: spectropolarimeter, 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 and a spectropolarimeter. We want to measure the magnetic fields in as many ways as possible. These are different wavelength range. Sometimes it's a grating instrument, sometimes it's an imaging instrument, but all of them do polarimetry to infer the magnetic field. And the one that I have in pink here is being built here in-house. It's built by the HAO. This is the heritage from the advanced Stokes polarimeter. It's the same concept. It's a much more complex instrument, but it follows the heritage from the ASP that we put at the Dan Solar Telescope. Now NSO is defining the science that we're trying to do with the facility. We have something we call the critical science plan. This is the science we want to do as soon as the facility is available for the community after commissioning. For a year and a half, we plan to do, and we're asking the community, you have this facility, what is the science you want to do? Here you have a number of science cases that we're considering for this critical science plan. I'm not going to enter into these details. What I want to do is to mention that this discussion happens at the science working group. And at the science working group, there are all of these members. There is people from Asia, people from Europe, and 17 from the US. These 10 are 10 scientists from the US. 2 of them from HAO. The director of HAO, Scott, is one. And one of the most fully committed scientists with the DICIS project, Phil Judge, is a member of the science working group, also from HAO. Then we have 4 COIs. There's 1 COI from HAO, the former HAO director, Michael Nolker. We have 3 US instrument PIs, and of course, for this, the instrument PI is Roberto Cassini, all of them senior scientists at HAO, and thank you very much for your support to the DICIS project. So you see, HAO is really heavily involved in the project, and that's a natural consequence of the evolution of our institutions. Before I end my talk, I want to go back to science. Science should always be the driver of what we're doing, and I think you all understand what I'm presenting in here. This is the WSA Enlil models where we have these clouds, these coronal mass ejections from the sun that sometimes hit the Earth. And they hit the Earth and they generate some level of geomagnetic storm. These clouds in here in this model propagate into a background that is magnetized. This magnetized Parkinson spiral, as you see it here, that gets the form from the cloud, comes from NSO's RAN GOM network. From our GOM network, the data is provided to these models, and you actually have a background that is magnetized. But the cloud itself is not magnetized. The cloud in the model doesn't have a magnetic field. Why? Because the input data is only this important data from SOHO, this is LASCO C3, and where you have velocity, you have density, you have some shape, but you don't have magnetic fields. So these clouds don't have any magnetic field included. What we need to do in order to get better models, of course, because these clouds are magnetized, is to provide the boundary conditions for the magnetic field. So what DICIS is going to do, and we know these clouds come from the filaments that get ejected from the sun. DICIS is going to go here. This is a filament that is being ejected here, observing the sunspot at the Dan Solar Telescope. And we want to do 100 kilometers or perhaps even more spatial resolution. We want to do 10 to the 4 polarimetry We want to do seconds because these evolve in really, really fast time. And with this, we will measure the magnetic field over a volume. Maybe we will be able to measure the currents and the Lorentz force, and we will be able to put this into the model and then predict the magnetic propagation of this cloud. I don't think Dickies is going to do a space weather prediction, but we really want to nail down what the physics is. That's what Dickies is going to do, and I look forward to do it with HAO. Thank you.
Thank you, Valentin. And any questions? We do have time for a lot, and there are a lot of things to ask about with DKIST and the neat science you'll be able to do with it. Yes, Yuri.
Since you said that the polarization changes with temperature, how do you keep track of that as the telescope warms up or cools down compared to when you put your big polarizer in front?
Oh yeah, I mean, that's an issue, actually. And when you put your polarizer, it's half of the light, okay, when you are going through the system. So what you do always is when you remove your polarizer, try to see if things behave the way you expect them to behave. We know a lot about polarimetry on the sun, so you can always go and see if there is residual crosstalk. And the residual crosstalk will come, you go to a sunspot, and there we know what it is, we know we should expect. There are some spectral lines that have specific properties that if there is any residual performance, you can correct for that. But that's an issue, and we solved it for the Down Solar Telescope. We didn't see actually any big effect. With DKIS, it will not be a problem. DKIS, actually, we don't have a 4-meter aperture linear polarizer to put on top. So we're not putting a linear polarizer in here. What we're doing are measurements about things that we know. Now we know a lot about the sun, about the polarimetry. So we just point to the sun, and we expect a number of things to be there. And some of them are real zeros that you can measure. And with that, you can calibrate for these residual crosstalk effects. But yeah, it's an issue. I mean, there is some art in here, and I understand how difficult it was and why it took so long for getting it developed, but yeah.
Any more questions for Valentin or DKIST? Okay, let's thank Valentin again.